Voice, you hear an echo also? Is it my voice is clear? Okay, okay. Thank you. ये अब चार्ज हो रहा है ना सर? ठीक ठीक ठीक. Okay, so today is the 4th day of the course, and initially today we will discuss a little bit about grid integrated wind energy conversion systems. So there are so many electrical machines, right? You have studied in your undergraduation. You have squirrel cage induction motor, wound rotor induction motor, and then DFIG, doubly fed induction generator you might have, and PMSG and synchronous electric motors. There are so many different types of machines which can be used for wind integration. But as you can see here, first we will see the wind energy highlights. Okay, then basically we will discuss a little bit about PMSG based wind energy conversion systems, and then doubly fed induction generator based wind energy conversion systems and the problems related with DFIG machine. If you have the series compensation, so we did some work in collaboration with Hydro-Quebec and IREC and those things. And then some standards and grid codes. All those standards and grid codes I will discuss in the second half of the lecture from 12 o'clock to 1:30 also. Then I will discuss IEEE standard 1547 also. So wind energy highlights, see, world's largest onshore wind farm. This is Ganzhou wind farm in China. Initially, around 10 years ago, I heard about it, and they were saying that it will be 20 gigawatt. But now we don't know how many. So I found out that it's around presently 8 gigawatt or so. And there are some problems. So I was in China for 2-3 weeks. I was visiting and discussing with some researchers. So they have some management problem in the farm, and it has to be transported, the energy has to be transported at long distance, then wind problem, and then there is another problem in China. That problem is of instability, voltage instability. So I was in China, I was discussing with their research big lab. They have hundreds of researchers are working, and then I visited many universities. So this is the problem. This is the problem, that when you integrate too much renewable energy, intermittent energy with the system, then it becomes a problem. Okay, so that I will discuss a little bit tomorrow also. But they have the voltage instability problem. Voltage instability caused by the intermittence nature of the renewable energy. So I was talking there, and then because you know the objective of global net zero is 2050. United Nations, they have conferences and those COP21, COP26, 29, and I think COP30 took place recently. So this is what we are discussing, that by 2050 we should have global net zero. Whatever we are emitting greenhouse gases, those should be absorbed. So global net is zero by 2050. This is what we were discussing. But so this is what I was discussing in China. But China has clearly said, no, they cannot reach that objective. So they have extended it to 2060. And why? Because this is the problem, voltage instability problem. They have so much renewable energy that now the system, they have voltage instability, and because of that, till 2030, they are focusing on thermal power plants. See, so the focus is a little bit shifted now to make the grid stable. So I will talk about this sometimes. So this is the thing. In China, perhaps they had initial problems, so that's why they are not going very strictly following that, okay, we have to reach 20 gigawatt, because they already have so much renewable energy. So this is what it is. So in this Gansu wind farm, 7,000 wind turbines with DFIG machines, doubly fed induction generator, from various manufacturers, Goldwing, United Power, Vestas, and 2,383 kilometers of HVDC transmission line. And there they have the mismanagement and those things. So this is what I came to know. But still it is the largest wind farm. Largest onshore wind farm in USA, Alta Wind Energy Center. So it has 1547 megawatt installed capacity, and they have Vestas wind turbine, 3 megawatt wind turbines, V90. I think 90 is perhaps the related with the, all the time I think about the French word, blades. In French we call it pal, so I was thinking pal, but blades, wind turbine blades, serving the needs of this much Californian home. Then, as far as I know, largest onshore wind farm in India, perhaps it is Muppandal wind farm in Tamil Nadu, 1500 megawatt installed capacity with 3,000 turbines, ranging in size from 200 kilowatt to 1650 kilowatt, from Enercon and other, Suzlon also, and Vestas. Perhaps what I think, why they have different sizes of wind turbine, perhaps it was developed in different stages, perhaps because of that. Earlier, it was not that a fashion to put very large, so perhaps they started with 200 kilowatt. This is what I think, that now with the development of technology, this is what is happening. Largest offshore wind farm, Hornsea 2, offshore wind farm in North Sea, UK. 1.32 gigawatt installed capacity with 165 Siemens Gamesa 8 megawatt wind turbines. And it is operational since August 2022. There are many other offshore wind farms under construction, like Dogger Bank Wind Farm. It is situated over 130 kilometers of northeast coast of England in North Sea. When completed in 2026, Dogger Bank will be the largest offshore wind farm in the world with an installed capacity of 3.6 gigawatt with Heliad X 13 megawatt turbines. Then Greater Shingwa offshore wind farm. This project involves 4 wind farms, Changwa 1, Changwa 2A, 2B, 4, located 35 to 60 kilometers of Changwa contain Taiwan, with total capacity of 2.4 gigawatt. Changwa 1 and 2A were commissioned on April 25, 2024, and the other 2 will be commissioned in 2020. Projects. So this is a picture of offshore wind farm. And then tourism is also taking place with the wind farm, like in Vancouver, Canada, we have this 1.5 megawatt wind turbine to have an observation pod. Okay, and then in Bahrain, you have World Trade Center, this tower with three wind turbines completed in 2008. Okay, so 225 kilowatt wind turbine is supplying 50% of the building power consumption. Then strata towers, 42-story skyscraper with 3 built-in wind turbines at the top. Okay. And then if you see the wind turbine, Siemens SWT 7154 wind turbine, 7 megawatt, it has 7 megawatt rated, very large size, medium speed PMSG machine, 75 meter blades, okay, the equivalent of 9 double-decker London buses, and swept area, you can believe it, this much swept area. Then Vestas V64 wind turbine, 8 megawatt rated power, medium speed PMSG. So all these large sizes basically are PMSG machine. 80 meter blades, equivalent of 9, okay, swept area, okay, and nacelle, 24 meter long, 12 meter wide, 7.5 meter high, weighing approximately 390 tons. So can you believe how difficult it is to build? And then Vestas, another turbine, 10 megawatt, okay, rotor diameter, see, 80 meter blades. Each blade weighs 35 tons. This is the swept area. And then Heliad, this 13 megawatt, 107 meter blade, 13 megawatt, okay, 248 meter high. Siemens Gamesa, 14 megawatt, world's most powerful offshore wind turbine. It was available, but I don't know who is using, if they have enough order for that, it's difficult to say. So world's largest wind turbine, Dongfeng Electric, 26 megawatt, I think it is still under construction, and they, because some companies, they announce in advance so that for future they are assured, okay, whoever is building wind, offshore wind farms, so they should keep this thing in mind that this machine will be available. So, and then Mianyang Smart Energy, 16 megawatt capacity, and another, I don't know what is this thing, 50 megawatt, but people want to get the publicity also. So now coming to the PMSG based wind energy conversion system. So what are the features of permanent magnet synchronous generator based directly driven wind energy conversion system? One important thing is the elimination of gearbox, because gearbox is always a problem. Almost 10% of energy is wasted in gearbox. Can you believe? 10% of energy is wasted in gearbox. And the maintenance of gearbox is not that easy. Okay, all the time, after 2-3 years, there may be a leakage of oil and those things. So you have to send, by helicopter, you have to send a person to go on the top of the turbine to fix. So it's not that easy. So that is the maintenance problem, because it is the rotating part, so some wear and tear in the rotating part. So those are the problem with the elimination of gearbox. Okay, so what actually, so if you remove the gearbox, what are the consequences? You use gearbox to increase the speed of the generator, because you have seen the blades are slowly moving like this, like maybe 15 or 20 turns per minute, right? But your generator has to run fast to generate 50 hertz or 60 hertz. So if you don't have gearbox, how will you increase the speed? You know the formula. N is equal to what? 120F by P, right? This is the basic formula, right? So if you have lower speed. So it means you have, to get 50 hertz or 60 hertz, you have to increase the number of poles because you are rotating with slow speed. So you have to increase the number of poles. So suppose you have 4 poles running at 1800 RPM, generating 60 hertz or so, but then your speed is not anymore 1800 or something like this. It may be much slower because there is no gearbox, right? So it means you have to increase the number of poles. So instead of having 4 pole or 8 pole, you have to have 80 pole or 100 pole or something like this, right? To have the same frequency, 50 hertz or 60 hertz, right? So if you increase the number of poles, then the diameter of the rotor will increase. So this is what is happening. Enercon has developed annular generator type PMSGs. They have the large diameter to accommodate even 100 poles or more than 100 poles. That depends what is the capacity of the machine. So the diameter, so there is the advantage. So if it is rotating with slow speed, it means very low wear and tear, so less maintenance, less losses. But I don't know about the cost. Perhaps it may cost more or something. That cost basically depends how many machine you are ordering. If you are ordering 5 or 10 machines, the price may be different. If you order 100 machines, the price will be different. So it basically depends on this thing. So, right? So elimination of gearbox. Then there is a work going on magnetic gears also. One of my colleagues is working on magnetic gears. So, but that is a costly thing. So you cannot put it on wind turbine. It will be very costly thing. So at that scale, 8 megawatt, 10 megawatt scale magnetic gear. So then variable speed operation for MPPT, this is available. If you have PMSG machine, you can have variable speed operation and you can extract maximum power. You can do MPPT algorithm and extract maximum power from the machine. No slip rings and brushes. This is a big advantage. This is permanent magnet machines. Now when we talk about permanent magnet has problems, and you know the problem. What happened in trade war recently? So Trump said, okay, 142% tariff on China goods. China said, okay, I am increasing 250%. See? And can you believe? Within a month, Trump came to the table. Why? Because they need rare earth materials. And I tell you, more than 90% of rare earth material is processed in China. So nobody can fight with China. All is controlled by China. If you want permanent magnets or other rare earth material, so you have to go to China. You don't have any, because it's not a simple work. Processing the rare earth, it pollutes the environment and contaminate people. So not every country will want to do. And then after that, when this happened, so Trump came to the table, everything was solved. Okay, so tariffs came down, everything came down with China. And with India, they were, oh, you are buying Russian oil, and then we have to increase the tariff of 50%. And what about China? You were fighting with China for so many years, and then now you are blaming India that you are buying Russian oil. And I tell you, US is buying so much uranium from Russia. They don't see this thing. But anyway, this is not our topic. But what I want to say that in 2011, I was doing one project with a company TM4. Now it is, they call it Dana TM4 in collaboration with Hydro-Quebec. And they produce powertrain for PMSM, electric vehicle. So in 2011, we had one project with them, And the engineer was saying it is so frustrating. At that time, 14, 15 years ago, it is so frustrating. Permanent magnet prices have increased 7 times in 1 year. In 1 year, the prices of permanent, perhaps China might be having some policy at the time, I don't know. So it was very frustrating for those companies which are making powertrain because the cost of permanent magnet will increase. And then there was one company, Molycorp, and it was listed in NASDAQ, and then prices of shares of Molycorp were increasing because they was working on permanent magnet or rare earth material. And then suddenly in 2015, it crashed. Molycorp shares crashed. Perhaps something might have happened. China might have given some statement or something. And now perhaps it is bought by some other company. But anyway, this is the thing. The China may control based on rare earth material, and permanent magnet is one of them. So they control more than 90% worldwide market on this thing. And then PMSG has enhanced fault ride-through capability. Low voltage ride-through, high voltage ride-through, or fault or some. So it has capability. Why it has capability? Because you have full size back-to-back converters. To converter, they totally decouple the generator from the grid. So that's why it has that fault ride-through capability. And then reduce copper losses due to use of permanent magnet. In rotor, you have permanent magnet, not any winding or those things. High power density, depends what kind of material, permanent magnet you have used. So these are the things which makes PMSG more efficient and reliable. So this is the thing about this. Now this is the basic control, grid connected. Here you have a grid, you have PMSG, this is wind turbine, back-to-back full size converter. So if you say you have 10 megawatt generator PMSG, then you need 10 megawatt this converter and 10 megawatt this converter, which may be a very costly. On the first thing is that machine itself is very costly, but you know, we always talk about, okay, permanent magnet machine is costly, but do you know how much, if you say the whole wind turbine, how much it will cost after all, the generator? So I was reading one article, so they said 20% of the cost of whole wind turbine is the towers. So what you make the towers? Another 20% comes to the blades. Okay, and if you come to the generator, it is 8 or 10% of the total cost. So generator is not that costly related to towers and blades and those things. But anyway, still you have full size converters, back-to-back converters, and then you have controller. This converter you can use to extract maximum power. So MPPT will be done on these things, right? Using some kind of control. There are so many MPPT control techniques, perturbation, observation, and other things. So extract power from here and bring it to the DC bus. So if you are not extracting power from DC bus, the dangerous situation may arise. The voltage may keep rising because energy is being pushed into the capacitor, DC link. So you have to extract that energy and send it to the grid, and that is the work of this converter. So it is basically the same type of thing which we have seen in active filters yesterday and before yesterday. What active filter? We have said that one objective of shunt active filter is to keep the DC link voltage constant. So how it will keep the DC link voltage constant? It will transfer the power from DC link to the grid. And then on top of that, this converter may work as a filter also, power conditioner also. So this is what I tell all my students. Okay, you have converter, inverter, they are not loaded all the time to their full capacity. Most of the time they are loaded up to 50% or so. So what you are going to do with the rest of the capacity of inverter, converter you have in the system, that capacity you can use for reactive power compensation, for harmonic mitigation, for load balancing, like power quality system. So basically, this inverter from DC AC, this is an inverter you are pushing, so that is fine, you are pushing the energy to the grid using this inverter, but at the same time it should work as a power quality conditioner also. So we integrate all the time, yeah.
So inverter और grid के बीच में कोई filter नहीं है?
What?
Filter.
Filter? No, this is, I have shown you a simple diagram. This is just a simple presenter. Otherwise you will have the coupling inductor, filters and those things. Just to show a basic principle, this is what is going on.
Other signal conditioning devices may be there.
Yeah. Well, always coupling inductor, capacitor, those things are there, filtering. But basically this inverter, suppose there is a load here, non-linear load. So what I wanted to say, that if it is a non-linear, unbalanced, reactive load, then instead of providing those harmonics or reactive power from the grid, why don't you use this inverter to compensate those problems? So this is why, so apart from transferring energy from the DC bus to the grid, the another, because it is not loaded fully most of the time, so the same converter, inverter, you can integrate those aspects in this. Apart from, you have, certainly you have coupling devices, yeah. So this is this. Generator side converter control, it means this converter. We are talking about generator side. So if you see here, so this is the power speed, this is output power, and this is the generator speed. This purple color, this is for mechanical power. Whatever power is produced, the wind is coming and the blades are rotating, so that mechanical power is going at the shaft, so that mechanical power. But the electrical power generated is not that much because there are rotation losses and other things. So basically for extracting maximum power, we use this curve, blue curves we have to use, not the purple curves. Okay. So from power speed characteristic, the maximum power at different wind velocity is almost a cubic function. So this is what we are seeing. This is the cubic function of generator. This curve is utilized to obtain torque command. So suppose we say, okay, this much power, this is the maximum power point. So you see on these curves, if we put a curve here, maximum power point, so basically this will be the reference generator speed. And then you can measure the actual speed. Okay, and then you have PI regulator, so it is giving the reference torque, electric torque, reference electric torque. You can calculate based on how much power. So you don't have to do calculation all the time. The MPPT, you can even use just this curve. Okay, and for particular turbine, because you see different speed, 12 meter per second here, 10 meter, so curves are different, 8 meter per second, 6 meter, 4 meter per second. At different speed, you will have different maximum power, so reference speed has to be changed. So that reference speed you may calculate using this curve, and this is the measured rotor speed, and this is PI controller, and this is the reference electric torque. Now for electric torque, basically this is the equation for this machine, and here see D axis inductance, Q axis inductance. But if we consider the cylindrical rotor, in cylindrical rotor LD is equal to LQ. So basically this term will be 0. So finally you will have this and this portion. So that's how, if you say we have reference electrical torque here, and you know all these values, so you can calculate reference Q axis current, which is proportional to the electric torque. So electric torque is proportional to basically the Q axis current, not the D axis current, Q axis current. So on the generator side, IQ is more important, and on the grid side, ID will be more important. So here we are talking about IQ, and you can set ID current to be 0 so that you can minimize the losses and maximize the torque. Okay. Now coming to the control of, okay, again generator side converter. So this is what PMSG, grid side converter. So you measure DC link voltage, you measure DC link current, IDC, VDC, multiply both, this will give you the output power. So this is the power basically which is coming to the DC link, voltage multiplied by current, that is the power here. So that power, then you use this curve, which is the topmost point of for each wind speed, where you draw this cubic curve, and from there P, whatever P is there, then corresponding reference speed, right? This is the reference speed here, or for this reference speed may be different. And then you measure the actual speed, and then you calculate, this is the PI and this is the electric torque using this equation. So electric torque, once your reference electric torque is calculated, using this term you can calculate IQ reference, and you can put ID reference as 0. Okay, and because you have measured the speed, you can integrate this, and this will give you theta angle. So then you can do DQ to ABC transformation. ID, IQ are there. You can get IA reference, IB reference, IC reference, and you can measure the actual current, and you can generate the signal. So this is the control, the simplest control. Otherwise you may get very complicated control and those things, there is no limit to make. This is just to explain, okay, this is the basic idea of this thing. Okay. Now if we talk about the grid side converter control, and you will be surprised and happy to know that you can almost use the same algorithm, basic algorithm, which we use for shunt active filters, because there also the same things are there, right? So this is what we did in shunt active filter also. We had the reference DC link voltage, measured DC link voltage, PI control, and it will give you the amplitude reference of the current. And then, like yesterday professor was saying, okay, you are using unit this template, and there is a problem in unit template, the voltage is distorted. Right, you are right, so that is the right way. But then, because it is a very simple control, this is otherwise you can use PLL and those things to get perfect sinusoidal, right? So you have unit vector, this unit voltage vector, measured voltage, divided by this Vt, and it will give you sine omega t minus 1, like same thing we saw in shunt active field for sine omega t plus 120. Okay, so this is UA, UB, UC, you multiply it by this and you get IA reference, IB reference, IC reference. So very simple control, and you can put it like this. Like same thing as in active shunt filter, we are putting the same thing. You are measuring this VA, VB, VC, calculating the unit vector for the voltage UA, UB, UC. Okay, you are measuring 3 grid currents IA, IB, IC, and here you see you have measured VDC here, you have reference VDC, PI controller. So this is the amplitude of the grid current, and you multiply it with the unit vector. This will give you IA reference, IB reference, IC reference, which are coming to hysteresis or PWM control, and you are measured current, and then you can generate the signal for grid side converter. So what is basically happening? You are trying to keep the VDC constant. So how you will keep the VDC constant? Because from the other side, power is constantly being shifted to the DC link, and your objective is to keep VDC link voltage constant. So power will be transferred from DC link to the grid automatically. And at the same time, your grid current, these are the reference and these are the actual, they will be kept sinusoidal. Automatically, all the harmonics which might be, suppose there is a load here, non-linear load, which is generating, which is non-linear load, harmonics are there. So it will automatically compensate, this control will automatically compensate for the harmonics or voltage unbalance, this current unbalance, not voltage, current unbalance and those things. So if you see the total thing together, so this is for grid side control converter, and this is for, no, this is for generator side. Generator is here, here it is grid. This is the grid side converter, and we have just put it together. Now there are lot of results and those things, just to show that this is the speed in RPM of generator. At that time your speed is increased, so you see the current of the generator, they are increased and frequency is increased. This is VDC, this is grid voltage which is constant and sinusoidal all the time. Okay, this is the load is 2 kilowatt. So why actually the student put 2 kilowatt load? Because he wanted to implement in the lab. So in the lab we were having 2 kilowatt machine. And then you see the speed is increased. So the power initially generated by the inverter supplied by the 500 watt, but because the speed is increased, so power output of transferred became almost 1500. So the grid will provide less power to the load. So this is what to show. The grid current earlier was this, now the grid current is reduced because the power was coming from the turbine, wind turbine. Okay, this is just to show these results. And there are some other results. And then just to show that wind speed is changing, so generator speed is changing, voltage and current of generator is changing. And it is just to show that this is the grid voltage, constant sinusoidal voltage, and this is the grid current, and this is the load current. Until unless this grid side converter was not started, your grid current was same as the load current. But as soon as grid side converter is started, it started doing the harmonic elimination, reactive power. So that's why the grid current becomes sinusoidal and less, because power is coming, see, apart from the fundamental component of the current coming from the inverter, you have harmonics also. So fundamental component, it will put more grid current. So this is what it is. So what you can do, you have the wind turbine or PVs, you can connect to the DC link of the inverter. Okay, and it is the same inverter. Increase the capacity of IGBTs which you are using. The size of the IGBTs will increase. So you see, this is what the student has done. This is the 4-leg grid interphasing inverter. This is the grid. This is the load. So you are measuring VDC, reference system, some kind of adaptive control he has used to generate ED reference. Unity power factor, okay, and then DQ to ABC currents and neutral current, compensate neutral current on the grid also. Okay, you have measured VAV, BVC, and then you have measured the 4 currents here, and then the control for this is produced. So what was happening was that in 2003, this IEEE standard 1547 came in 2003, and we were so much, because almost at the same time we started working, because earlier we were working on this power quality thing. We started applying the same technique which the 20 years ago, we started working on this renewable energy integration. And then at the same time, this 2003 IEEE standard 1547 came. So initially we were happy, okay, some standards are there to integrate distributed renewable energy sources and those things. There at the time, I think they were calling it variable energy sources, some other term they were using instead of DER, they were using some other term. And then in those 1547 IEEE standard at that time, they said, okay, as soon as any disturbance comes on the grid, you have to disconnect. You have to disconnect your PV, you have to disconnect your wind turbine. What is this? This was all nonsense. So we were fighting in IEEE on those things. Why you are putting those things like this? Because those are generating power. If you need some frequency assistance or load assistance, they should be helpful to you. And instead of helping, you are disconnecting them. And this is what it was there in 2003. I will discuss that after the break. I will discuss about IEEE standard 1547. So we were not happy. At that time, we were working. And see, this is what is happening here. These renewable energy sources were supposed to supply only active power. They should not touch the reactive power. They should not touch the harmonics or any other thing. right? This is what actually the voltage sag, voltage swell, those things, you are not concerned about this. They were told to the wind farm operator, okay, disconnect your wind turbine, disconnect your PV. And so what was happening, that this renewable energy sources were supplying only the active power. So if you have a load which needs active power, harmonics, reactive load, so everything was coming from the grid. That was the problem. Now what was happening, that if load is there, your renewable energy sources was providing only the active power. So all the reactive power, harmonics, those were compensated by the grid, so grid became polluted. That was the problem. Grid became polluted because all the harmonics are coming. So what is the use of having such a good quality inverter there? You have an inverter there. Why don't you use that inverter used in the renewable energy? So this is what the work we did. And we were fighting for this all the time. And then we suggested at that time, long ago we suggested this thing, and that was the effect that in, I think, 2018, when the new IEEE standard 1547 came, then they integrated those things what we were suggesting 10 years ago. Okay, so here you see, this is the grid, this is the load. Load needs active power, harmonic power, reactive power. So, because the inverter, interphasing inverter used with PV and wind turbine, which was already loaded, only loaded up to 50% or 60% of the capacity, it was just lying there, that capacity. So we used that capacity not only to transfer active power, but to compensate harmonics and reactive power also, so that the grid became less polluted. So this was the very pioneering work we did many years ago, and finally the fruits came, and in the form of new IEEE, updated IEEE standard 1547. So here you see the, oh, chai? Okay, chalo chai pite hain. Okay. अब ठीक है भैया? So we will continue with our discussion, and we were discussing the control, and these are the simulation results. Okay, so you can see grid voltage is perfectly sinusoidal and of constant amplitude. But if you see the load current, it is highly nonlinear, unbalanced nonlinear current. And this is the inverter current. So what is the objective of this inverter? That it is fine that it is whatever energy is generated by PMSG, it is being injected into the grid. So this is one thing. So here you see this current is of inverter is unbalanced and some harmonics are there. This is to compensate this thing. So it is, this current is generated in such a fashion that grid current is perfectly sinusoidal. And if you see here, you will see that it is in phase opposition of this voltage. Okay, it means the current of the generator is being pushed into the grid. So voltage and current in phase opposition means the power is going inside the grid. See this very interesting result. This blue is the grid voltage, and ILA, red one, this is the phase A of the load current. And you see IA is the grid current, blue. So you see this current is in phase opposition of the grid voltage. It means it is not a load, it is the current power generated and pushed into the grid. Okay, and this is the load current, and inverter current, you see the green is the inverter current. Why it is non-linear? Because it is taking care of the harmonics. So that's why it is cancelling all the harmonics, plus it is giving the fundamental component of the current. You see the line neutral current, this one is the neutral current of the grid, and this is the inverter current, this one inverter neutral current. So it is cancelling the grid neutral current, this load neutral current. So if you see the grid neutral current is 0, because load neutral current is being cancelled by the inverter neutral current. So it is compensating for zero sequence current also. So student did the experimentation work also, and here you see the grid currents. These are highly nonlinear. It is just to show active filtering mode of 3-phase 4-wire nonlinear unbalanced load compensation by the grid side converter. So as soon as grid side converter is put on, all these non-linear grid currents, they become sinusoidal constant current. And these are the inverter currents of phase A, B, C, and the neutral current. So if you see this portion here, it is shown here. So see, because it is cancelling the harmonics and pushing the, so this is the current injected by the inverter. This is inverter in wind power injection mode with 3-phase 4-wire nonlinear unbalanced load compensation simultaneously. So simultaneously it is injecting power as well as doing the filtering also, inverter. So this is the grid voltage of phase A, grid current, phase A, load current phase A, inverter current phase A. So if you see, explain it here, this is the grid volt phase A, which is constant sinusoidal. This is the grid current for phase A. It is because inverter current of phase A is injecting the extra current. So that's why in this part grid current is reduced, because extra current is coming from the inverter. So the load current is constant. And here also you see grid voltage and current, load current, inverter current. And if you expand this portion here, this is the grid voltage, this is the grid current. Before the starting of grid inverter, grid current were distorted. But as soon as you started putting, it becomes sinusoidal and in phase with this thing. Now, speed and position sensorless control of PMSG. Earlier we had measured the speed and those things. Now we are talking about sensorless control of PMSG. Precise information about rotor speed, position is essentially required for the vector control of PMSG, right? Generally shaft mounted speed and position sensor, as you might have done in your laboratory. Use of sensors may result increased cost and complexity, time-bound maintenance, tearing and wearing of mechanical parts and connected lead, false operation of sudden breakdown. So these are the problems if we are using mechanical sensors for position and speed. So to alleviate the need of sensors, several speed and position estimation algorithms have been given. So there are many more other algorithms which may compensate and where you need not to use speed and position sensors. You estimate those things. Speed and position estimation may suffer because it may have some problems also in estimation. Ignorance of parameter variation, rapidly changing weather and operating conditions, distortion in current and voltage signals, inaccuracy involved in low voltage. So there are many problems. But this adaptive neurofuzzy inference system technique developed by a student, it has certain advantages. So this is what actually sensorless control of PMSG was done. So you are not measuring position or speed of the generator. You are just measuring the voltage and currents. Even the student said, okay, we can avoid the use of third current sensor because the sum of all the current are zero and voltages and current are zero. So then VA, VB, VC, you have IA, IB, YC, and then you have ABC2 alpha beta Clark's transformation to, actually it should be voltage alpha and voltage beta. It should be current alpha, current beta. And then he used ENFIS system control algorithm for position and speed estimation. So position and speed estimation was done. So on the DC link, so this is grid, this is generator side control. Okay, so you are measuring VDC, IDC, which is giving you power at the DC link. So you use this for MPPT, which will give you, which we have already discussed, reference speed. This is estimated speed. Using PI controller, it will give you IQ reference. ID reference should be 0 as we had discussed before. And then DQ to ABC transformation. And here reference current for phase ABC. And these are the measured current. So this is how you generate the signal using PWM. And then those are the, I think I have less time, so I should speed up. So this is the error in speed estimation. The student did small errors while the ramp is there, and position was okay. And then these are hardware implementation. So I will speed up, I will not explain those things. Now coming to doubly fed induction generator based wind energy conversion system. So as you know, this is basically a double wound induction machine, right? On the rotor side, you have winding, on the stator side, you have winding. Stator, you are directly connecting to the grid here. This is the wind turbine and the gearbox. This is a gearbox. Actually, DFIG machines in my home province of Quebec, in 2007, they started putting the wind farms. And they started using doubly fed induction generator by the General Electric Company. And its capacity, I think, was at the time 1.5 megawatt machines. And then they were using 500 kilowatt rotor side converters, these. So if you are saying this is 1.5 megawatt, this is 500 kilowatt. So this is the advantage, the cost is reduced. First of all, DFIG machine is cheaper than PMSG. Another thing, the inverter, this is 1/3 capacity, variable speed range is from this, gearbox is there, bidirectional back-to-back converter, okay. So what are the overall advantages of DFIG fed wind energy conversion system? Reduced converter cost, as the converter rating is typically 25 to 30% of total system power rating. Improved efficiency due to reduced losses in power electronic converters. Suitable for high power applications. Bidirection flow of reactive power. High fault ride through capability during network disturbances. And flexible 4-quadrant operation with precise control. This is the advantage of DFIG based wind energy conversion system. So if you compare this DFIG, PMSG, so this is what actually we call it wind energy exploitation technologies. So there are type A, type B, type C and type D. Type A is basically squirrel cage induction generator based converters, this wind energy, that is type A. Because if you are not using full size inverter converter, then it is difficult to do the MPPT. Then you have type B with wound rotor variable resistance machine. This is again induction machine, wound rotor induction machine. Like here you have squirrel cage machine, here you have wound rotor induction machine. And then PMSG, type D and type C. D is the best, this is what they classify because it is give the, so how you can compare pros. If you are using DFIG type, you have a variable speed, reduced converter rating, this is the advantage, right? Active and reactive power control. For PMSG, variable speed okay, direct drive, this is the advantage, active and reactive power control, complete grid isolation, no external excitation. While in DFIG, you need slip rings. Okay, wound rotor variable, you have small speed range control by rotor resistance variation. This you might have studied in your undergraduation, okay, you change the rotor resistance, right? So the characteristic is something like this, right? So if you change the rotor resistance, this is the quadrant 1, 2, 3 and 4, right? This is motor, generator, generator. So by varying the resistance in the rotor circuit, basically you are changing the speed. This is what it is basically, wound rotor you are putting, because maximum torque, this is the advantage, right? By rotor resistance variation, you might have studied induction then motor. Basically, you have maximum torque here. Anyway, so if you see the disadvantages with defig machines, you have gearbox. So we have already discussed there are so many losses and maintenance costs and those things with gearbox. Need for slip rings. Slip rings are okay, there are 3 slip rings and 3 brushes. They need clearing up, cleaning, maintenance of brushes and slip rings, right? This is the disadvantage in defig machine. While PMSG disadvantage, full converter which costs a lot, because back-to-back full-size converter. Here you have 1/3 cost. High cost of PM material, risk of PM demagnetization. If you have wound rotor type, losses in rotor resistance, active power consumption. SCIG, simple and robust construction, low cost. This is the advantage, but the disadvantage, active power consumption, no speed control possible through rotor. Yeah.
Sir, in type D, complete grid isolation is possible.
Where?
Type D.
Type
Type D.
D.
PMS, yes. Complete grid isolation is possible.
You are talking type D.
Type D. PMS.
PMSG, yeah. Demagnetization is.
No, complete grid isolation.
Yeah.
But sir, why it is not possible in C?
Because their stator is directly connected to the grid. You see? Here, the stator winding is directly connected to the grid here. While in PMSG, you have back-to-back full-size converter. So when stator is directly, so this is the problem. We will discuss this thing. What is the problem if stator, because stator has the inductance. And what will be the problem if we have a long transmission line connected to this machine, then that long transmission, if it is more than 150 kilometer, then you know the equation. We will see this P is equal to V1, V2, X, L, sine, delta. This is the basic equation, right? So if you have a long line, so this XL is large, so power transfer may be reduced because of this. So that is why we do series compensation. So we will come up that then if we do the series compensation, then it may have exchange of energy with the this motor winding, stator winding. So that problem we will come later. But to answer your question, this defig stator is directly connected to the grid, while in PMSG you have full size back-to-back converter and you can have isolation. Okay. So this is the thing, back-to-back converter here. Power, so you see bidirectional power flow can be here, bidirectional active and reactive power flow. Rotor side converter, defig control, active reactive power, grid side converter, DC bus, power factor. So you see this grid side converter, again, this is fine. You are trying to have DC is constant through this by active filtering. This is what we did in shunt filter, right? We tried to keep VDC constant. So here this converter can take care of power quality problems, power factor and PCC, at PCC. So here you have PCC somewhere. Now, challenges posed by interaction between defig and the grid. So you see, this is your wind turbine with defig and back-to-back converter. Stator is connected here. So this is the line resistance and inductance, and you have the series compensation here in series. So we will come to that. So you can do maximum power point tracking as we did in PMSG, okay. sensorless operation is possible here, and you can estimate position and speed. If you can do direct power control and vector control, you know the advantage, disadvantage. And then voltage and frequency support. This is the thing, that it can support voltage and frequency, so it should remain connected, okay, by providing active and reactive power. And fault ride through capability. So if there is a fault, it should be able to, there are some, we will be discussing IEEE standard 1547. Subsynchronous resonance, this is what I wanted to tell you, that you have this, so this P is equal to V1, V2 divided by XL sine delta, this is what you use, right? So if it is long line, maybe 200 kilometer or so, then inductance of the line increases and it limits the power transfer. So how you increase the power transfer? You reduce the inductance by putting the series capacitors. So it will become XL minus XC. XL minus XC. So the total reactance of the line is reduced, so you can transfer more power. So this is what actually happened, that around 40 years ago, Hydro-Quebec had the long transmission lines, and to increase the transfer power limits, they put the series capacitors in line with, in series with the line, series capacitors. So now they have series capacitor for last 40 years. And then 20 years ago, they started integrating wind farms based on doubly fed induction generator, where stator is directly connected to the grid. So this is what they were worried about. And they asked me to investigate this, how it will affect. So one of my PhD students worked on this thing. There is a possibility of some subsynchronous resonance. Resonance at below synchronous speed, frequency. There may be exchange of power between the electrical transmission energy and the mechanical energy, exchange of power, and because of that, oscillations will take place, and they are called subsynchronous resonance. Okay, so subsynchronous resonance, there is a possibility. So it will particularly harmful for mechanical components. So around 50, 60 years ago, in United States, there was a big generator, I think more than 100 megawatt generator, and there's a shaft, its shaft was broken. Because of this subsynchronous resonance, oscillations were taking place because of the exchange of energy from the grid transmission line and the mechanical exchange of energy, and because of the oscillation caused by subsynchronous resonance. Okay, long transmission, see, more than 150 subsynchronous risk of sustained oscillation at subsynchronous frequencies. Then there is a model, my student modeled DFIG in detailed with all these D-axis and Q-axis, those things. It modeled the transmission line with those capacitance, whatever series capacitance they were, Hydro-Quebec was having, and he made the model. And then he modeled the machine also, turbine generator, mechanical model, which was very important. So generally, the researchers, they take two mass spring model of rotor and hub blades they put together, which has 2 Hz of frequency. for 2. But he included the blade flexibility also. So this was not done by other researchers, but because you know the blades are moving, there is a flexible and there is dynamics related with those. And because of that, he found 2 Hz and 12 Hz frequencies with 3 mass system. This is what actually the problem is. So if you simplify your model of machine, that may not give the, this is what we wanted to see. So what he did, he configured 3 systems, SA, SB, SC. So here there are 3 machine in the wind farm. He considered 3 machine. Otherwise, many researchers, they consider, okay, wind farm is 1 machine and then the whole system is there. So why to bother about so minutely modeling everything? But he took 3 machine wind farm, 3 mass spring mechanical model also he considered. And he said, okay, geographically, because wind farm is a big area and many kilometers, so wind speed may be different at different places. So he considered 3 wind speed at 3 different machines, 8 meter per second, 9 meter per second, and 10 meter per second. And power output at 300 megawatt base, he said, okay, 0.75 per unit, he will take the power output. Now, in second modeling, he took single machine wind farm, which generally people do, but other people, they take 2 mass spring, but he took 3 mass spring model. And he took 9.2 meter per second and the same power level here also. Then the third model he took single machine wind farm, 2 mass spring model. Okay, so same speed and same power. So you see, this is what happened. Simulation result for SA, it means 3 machine with 3 mass spring model. Okay, so at different interval, he started increasing the series compensation. Here is slowly he is starting series compensation, and some oscillations were there, but they subsidized. But at this point, 27 seconds, so this is the power, active power and reactive power, this is the turbine speed. So at both places you can see at 27 seconds, when compensation level reached 73%, series compensation, we are talking about series compensation because we were worried about series compensation, we slowly increased the series compensation. So you see resonance took place. Grid natural frequency was 13.5 Hz and turbine natural frequency was 12 Hz. So 12 Hz was very close to 13.5 Hz, and because of that, exchange of energy was taking place between the grid, transmission grid, and the mechanical oscillation. So that's why these are the subsynchronous resonance. He could able to notice this thing. Now he, in the second model, he took 1 machine, but three single machine and 3 mass spring model. So again he did the same experiment, and in this case he could see the subsynchronous resonance at 43 seconds instead of 27 seconds, because he simplified the model. So he could go up to 43 seconds with 83% compensation, series compensation. And he noticed grid natural frequency at 10 Hz and turbine frequency 12 Hz. So they were very close by, so that is why resonance was taking place. Then in third case, you can see that he kept increasing the compensation and subsynchronous resonance is not triggered after reaching 83% of compensation. And grid natural frequency 11 Hz does not interact with turbine 2 hertz, because now you are talking about 2 mass spring model. So there 13.5 hertz frequency was not there, there was only 2 hertz frequency. So it did not interact with 11 hertz. So you see, this is what actually, if you are doing a particular application, you have to see what are the important parameters. It was verified that higher compensation level increases the risk of SSR phenomena. So if you increase the series compensation, there is a possibility that subsynchronous resonance may take place. The risk of resonance directly relates to low machine speed. This is what he noticed. In SA, the lowest wind speed was 8 meters per second, drove the respective turbine cluster into resonance at 73%. The 2 other clusters follow shortly. In SB, 83% compensation level is reached before undergoing SSR in single machine representation. So you see, this is what he noticed. So that's it. These are, I need not to discuss this thing. Perhaps I can continue for next 1 hour. Yeah. I can continue till 1 o'clock. I can continue, right? Okay. So here I have put some slide for standards and grid codes. These are not IEEE standard 1547. It is in general, it is speaking about grid codes and those things, what are and why they are so grid codes and those things. Okay, if you want, you can go through this. But now I want to discuss, because I have to finish at 1 o'clock. So I will discuss what is this? Yeah, configuration control of grid connected PV systems. Okay. So there are many interesting things I will discuss, and you already might be knowing those things. Why solar, impact of solar energy in Indian energy scenario, solar potential in India, solar power scenario in India, application of solar. So many things you know, and there are some interesting things. Why solar? Because it has a limitless energy. Okay, so there is nothing. As the publication Renewable Energy Info estimate, the Earth's surface receives 120,000 terawatts of solar irradiations, which represents 20,000 times more power than the whole planet needs. Okay, so that's why the solar energy is very important. Solar power is good for the environment. CO2 free power source, the environment impact of solar power is significantly smaller than other power generation methods. The impact is mainly related to the production and supply of special material that requires produce solar panels. So this is the issue. Basically, when you are producing solar panels, perhaps it may have some environmental impact. And after 20-25 years, when you recycle them, then perhaps the work is going on in this direction, how to recycle them and those things, but it may have environmental impact. Solar power can use underutilized land. Across countries, there are vast land that are far away from big cities, capital. So with solar power, we can actually make use of land and subsequently generate great value. Okay, solar power causes less electricity loss because electricity needs to be transported from big power plants, you know, thousands of kilometer transmission lines. So there are losses. Long distance transmission line equal power losses. While rooftop solar panel is just there near the load, so there is not any loss. It increases the electricity efficiency considering the short distance. Your energy becomes domestic, and as a result, you are in control of your own bills and energy usage. Solar power creates jobs and economic growth. Our national economy can be helped by solar power. The more people who opt for solar, the more needs will be for companies to install solar panel. This creates additional jobs for skilled workers and consequently keeps the economy growing. Boost energy independence. The sun is near infinite source of energy and a key component of achieving energy. By increasing your capacity to generate electricity from sun, we can also insulate our country from price fluctuation global energy market. So this is what actually we want, the more and more EV market. So we have solar energy, which is almost free, and then you have more and more, then you will have less consumption of diesel and petrol and those things. So you will be less dependent on other countries. Drastically reduce or even eliminate your electric bill. Yeah, this is a very interesting thing. I want to tell you, very interesting thing. I was, 2-3 years ago, I was talking some of my friends in India, and they told me that they installed, 4 years ago, they installed solar panels. Someone installed 5 kilowatt, another one installed 10 kilowatt solar panels. And they were saying within 4 years they recovered their money because there are some government subsidies, and they have less electricity consumption bill. So they were able to save money, and within 4 years, now I tell you very interesting thing, that around 5 years ago, I was talking to one of my friend in New Jersey, and he told me that he put 10 kilowatt solar panel at the roof of his house. And within 5 years, he recovered his money. Because he was selling, during the daytime, he was selling his electricity to the grid, and he was able to save money. Now, I also became interested. So 3 years ago, I thought that I should also be a good citizen, and I should install solar panel at the roof of my house. So I was just looking for contractors and those things on online, and suddenly I saw there was one link, and Hydro-Quebec is the utility company in the province of Quebec, right? They provide electricity. So I went to that website. So it was, before you install solar panel, you should know the facts. This was the title. So I went through. So what it was to calculate how much it will cost you to put the solar panel. Okay, so I put, okay, I need suppose 10 kilowatt solar panel to put, and then it asked me what is your geographical, I told my city name and those things. Then it calculated everything, and it was costing me around $30,000 to put 10 kilowatt solar panel. And then it estimated how much time it will take you to pay back that money. And it was, you will survive, it was 28 years. 28 years it will take me to pay back my expenses of $30,000 if I put 10 kilowatt solar panel at the roof of my home. Can you believe it? Why it is so? My friend in New Jersey, he was able to pay in 5 years. Why here in Canada and Quebec, it will take 30 years, and the life expectancy is perhaps 25 years. It means I will never recover my money, right? So there is a reason for this. In California, I have a friend. He said he was able to recover in 3 years the money. Why it is so? Because in New Jersey, the electricity price is around 20 cents per kilowatt hour. In California, perhaps it is 30 cents per kilowatt hour. In New Jersey, it is 20 cents. In California, perhaps it is 30 cents. But in the province of Quebec, we pay 7 cents, 8 cents per kilowatt hour. So even if we generate the electricity, we will not get that much money. So that's why it was taking so long. So why electricity is so cheap in the province of Quebec? Because we have 90% is hydropower, which is very cheap. Okay, and then 10% is the wind energy. So 100% electricity in the province of Quebec is already renewable energy. So I'm not helping my province by putting solar panel because 100% already it is a renewable energy. But they did not understand, and I wanted to talk this thing to higher administration Hydro-Quebec, that Quebec sells electricity to United States, and so it sells when they need during the summertime, when there is a lot of heat, so for air conditioning, and then when the prices are cheap, they buy back. And so this is what Hydro-Quebec and Quebec there, and they make $3 to $4 billion every year in this process by selling electricity and buying electricity from. So what I wanted to tell them, okay, buy my electricity at higher price, sell it to US. So why 7, 8 cents? Give me 12 cents or 15 cents so that at least I may recover some money, but they don't understand this logic. But anyway, so you see, this is the situation. But here in India, even if you don't produce 100% of energy you consume, solar will reduce your bill, utility bill, and you will still save a lot of money, but not in Quebec. Earn a great return of your investment. Impact of solar energy in Indian energy scenario. There has been a visible impact of solar energy. You already know these things. Solar energy-based decentralized and distributed application have benefited millions of people for cooking, lighting, and other energy needs. Social and economic benefits, reduction in drudgery among rural women and girls engaged in collection of fuel wood. Because I remember when I was small, we used to see that poor girls used to come to our farms and collect the wood from there and sell. This is how they used to save money. But now that is not necessary. Minimization of risk of contracting lung and eye ailment, employment generation, so improvement in living standard. So you know already all these things. Solar energy sector in India has emerged as a significant player in the grid-connected power generation. It supports the government agenda of sustainable growth while emerging as an integral part of the solution. Okay, so see, solar potential in India. Here you can see that it is more than 2000 kilowatt hour per meter square. So you see, this is so much potential. And statewide estimate of solar energy potential in the country, in Andhra Pradesh, this is the solar potential. In Rajasthan, check 142 gigawatt peak, lot of energy. This is the potential. Okay, Gujarat, and see Jammu and Kashmir, MP, so much potential of solar energy in India. About 5,000 trillion kilowatt hour per year energy is incident over India's land area, with most part receiving 4 to 7 kilowatt hour per square meter per day. Lot of energy. While in Canada, I think it was 1100 kilowatt hour. It is per square, 1100 kilowatt hour per kilowatt installation. This is the yearly potential. India has solar potential of 740 gigawatt, assuming 3% of wasteland India. And I was in China. China was already, I thought that China was generating 650 gigawatt of solar energy. So I was giving a presentation in China in a company. There were many engineers sitting. I was telling, okay, China is doing so great, 650 gigawatt of solar energy is produced. But engineers said, no, this is not correct. Now it is crossed 1 trillion. So see, this is what is happening in China. So India's largest solar PV power plant, Bhadla Solar Power Park, 2,250 megawatt in Rajasthan, Jodhpur district, spanning 14,000 acres. So you can see this photo, amazing. And then second largest Shakti Sthala solar power plant, 2,050 megawatt, located in Pavagada Taluk in Karnataka. Okay, 13,000 acres of land. This is vast, you can see. Amazing thing. And then the third one is Ultra Mega Solar Park, 1,000 megawatt, located in Andhra Pradesh. Area around 6,000 acres. Okay, this is NP Kunta Ultra Mega Park. Okay, so you can see, because we are short of time, I will just forward this thing. Still renewable power. So then there are many applications around the world. What are the application? Parking meters we have like this. At many places they are being used. Traffic signals, telecom, towers, water irrigation pump in India. I think Shakti pump, they are making this thing, right? Street lighting, solar parking, power in space. Even what happened to Chandrayaan 3, I think it was Chandrayaan 3, it landed on moon. It was Chandrayaan 3, right? Which landed on moon. And it was working fine, I think, for 1 week. And then it was shut down. Why? Perhaps they were expecting, because it was dark area, and they were expecting that after a few days, perhaps solar radiations will come and the battery will get charged, but it never happened. So perhaps they could not revive it. Because of the low temperature also they had. So it was so sad to see. But anyway, whatever experiment India wanted to do, they were able to do it. Then solar windows and solar roof tiles for military uses, transportation, and this is the solar energy conversion. You already know this is grid tied. Okay. Residential off-grid, grid tied. In solar power integration. So what are the technical challenges? Voltage fluctuation, harmonic, DC offset, same thing which we have power quality issues, right? Reactive power, voltage regulation, low power factor, neutral current compensation, load manager. All these are power quality issues which we had discussed. Classification of solar energy. So you have a standalone system, which we will be discussing tomorrow, and grid interface. So in standalone, you have single phase and three phase. With grid interface also, you have single phase, three phase. Okay, single phase, single stage and two stage. Same thing with three phase, three wire, three phase, four wire, but single stage, two stage. See, all the time single stage, two stage, and then topology and control. So this is common for everyone. So you know the characteristic of PV array. This is the power output, and if you change the insulation, so this is the curve for 1000 watt per meter square. If you increase the solar insulation 300 watt per meter square, so power will increase 500, this curve 700 and 1000. So you see maximum power point tracking you can do. Change in short circuit current, same way in the current you can see 100 watt, 300 watt per meter square, 500 watt. So as you increase the solar radiation, this current level will increase. Change in open circuit voltage, change in MPP voltage, need for MPPT controller. The MPPT, you have so many control algorithm. So, and then time domain control, these are same control algorithm which we saw for reactive power, this power quality also, the same control algorithm. They are applied everywhere, okay. Already we have seen, so in time domain and then frequency domain, we have already seen these things. Now system configuration of single stage, single phase. So you have single stage, so you don't have DC to DC converter for boost to have the DC voltage constant here. You directly connect PV inverter and then you integrate it with this. This is single stage grid tied PV inverter. So this is control algorithm. You measure the voltage and current of the PV, MPPT control, any algorithm. Then you have DC, VDC reference, power generated, power, active power, and here you have VDC measured, averaging, and here you have VDC reference and PI controller, and you have here the current loss. Here you measure the source voltage. This is in phase and this is in quadrature, and you calculate amplitude. This is unit vector, and then here you have source current, PV current, and minus the losses. It will give you the amplitude of the source current multiplied by unit vector. So this is the reference current, this is the measured current, and you can control the switches. And these are some experimental results. I have to finish at 1 o'clock? Oh, okay. So I will not go with this test. Then you have single stage, 3-phase grid tied. So instead of single phase, you have 3-phase here. 3-phase 4-wire. So you see you have neutral also here. Neutral can, so you need extra leg, and still it is single stage. Okay, you have having diode here. Comparison between single stage and 2-stage PV systems. So if you see single stage PV, fewer parts, no separate DC-DC, because whatever voltage is coming. But what happened few years ago, one of my master student was working on a project, and we were talking about single stage converter for PV integration. Then he was able to integrate the DC voltage constant in inverter itself, like we do in active power filter. So he modified his algorithm so that otherwise single stage you say, okay, voltage coming from the PV is varying and those things, but somehow he was able to do something. So here you have more parts added to DC stage because you want to keep the DC link voltage constant, so you need DC-DC stage. Efficiency here slightly higher for single stage, fewer stages, and slightly lower extra stage losses. Cost, lower hardware cost, while in 2-stage you have higher hardware cost. MPPT performance, weaker MPPT under fast changes. And here is stronger and more stable MPPT because you have an extra DC-DC stage. DC link capacitor, larger capacitor, more ripple energy is there, so you need larger capacitor, while in 2-stage you need smaller capacitor possible. control complexity, single more complex controller, split loop, simpler per stage, power quality, slightly higher THD but compliant, better THD here, 2 stage and clean and grid, reliability and size, higher density, fewer parts, larger, more parts but less capacitor stress. Okay, so this is 2 stage, 3 phase, 4 wire example of 2 stage grid connected PV. So 4 wire, okay, for neutral also. So this is the non-linear load. Here you have a grid and this is the neutral wire. So this is the extra you have, and here you have DC-DC boost converter to keep the DC link voltage constant. Single phase grid connector SPV base. Okay, so here you add the battery also. Okay. Now power management scheme. What is the operating mode? Is it islanded mode or it is grid connected? So if it is grid connected, battery is in floating condition and PV power is transferred to the grid. But if it is in islanded mode, you have to see that state of charge of battery is between minimum and maximum value. If it says yes, so power, if then PV power is more than load power, if it says yes, then battery charging and MPPT operation. If PV power is less than load power, no, then battery discharging and MPPT, because you are getting less power from PV. Now state of charge of battery is not in between this, then you have to see state of charge of battery is less than minimum. So if you say yes, then you have to do load shedding because there is no power left in battery also, right? If it says no, then state of charge of battery is more than maximum of MPPT operation. So this is the power management. Summary of solar energy converter system: increasing demand for PV power for central and distributed generation. Government incentives has further increased the popularity of a small scale PV system. Classification of various VSC based single phase and 3-phase configurations have been investigated for feeding. The multifunctional PV and VSC simultaneously help in power quality improvement. Okay. So I have around half an hour to finish this thing, IEEE standard 1547. So IEEE standard 1547 for interconnection of distributed energy resources. Okay. So we will see the introduction, historical background, context, these things we will discuss. The growth of distributed energy resources, including solar photovoltaic system, wind turbine, fuel cells, battery storage, has significantly changed the operational paradigm of modern power system. Unlike conventional centralized power plants, DERs are often connected at the distribution level. Okay, you have solar panels and roof panels, right, closer to end users. This distributed integration poses technical challenges such as voltage fluctuation, frequency deviation, bidirectional power flow, increased risk of instability. So this is what we call distributed energy resources causing problem. To ensure safe and reliable operation, IEEE 1547 standard was established originally in 2003. Okay, so this is what I was talking about. It set basic requirement for performance, testing and safety. And then it was updated in 2018. and it introduced advanced functionalities which we wanted 15 years ago, but they did it in 2018. Because, this is very complex process to have standards, because there are so many companies and researchers around the world, they are involved. So it is very difficult to bring a consensus of all the people, because everybody has the interest, especially the companies making this thing. So introduce advanced functionality in 2018, which were not there before. For grid supportive inverter controls, this is what we were asking them 18 years ago, because we said that PV and wind should support the grid, not disconnect them. Right-through capabilities, okay, and communication protocols enable DRs to activate, contribute to. So now this is done in 2018. 2003 edition was in safety and simplicity. DRs were required to disconnect at that time in 2003 standard rapidly during abnormal grid condition, voltage and frequency, to prevent islanding or equipment damage. This ensured safety but limited DR's ability to support the grid. With the rising penetration of DR, so suppose you say, okay, 50% energy is coming from the PV and wind, and if there is a problem in grid, are you going to disconnect it? 50% of energy. So it is all, everything will be blackout. To address this, 2018 edition redefined DR interconnection by introducing grid supportive behavior. See, DRs must remain connected during short-term disturbances right through. Inverters must provide voltage and frequency regulation instead of immediate disconnection. So now it is there. Communication and interoperability were made mandatory to enable coordination control with utilities. The development of 1547 is driven by several key factors. Rapid expansion of renewable energy sources. I don't know how much, we will talk about this perhaps tomorrow, but in China, I think it is already 79% of total energy is renewable based. So China is much ahead. Okay, in India, I think it is now perhaps more than around 50% or so. Prior to IEEE 1547, utilities often had their own procedure leading to inefficiencies, like hydro, Quebec was having different rule, and then Manitoba Hydro had different, and Alberta had different, in different provinces in Canada they had different rules. And still they follow their own rules. They don't care about IEEE 1547, but still they have to reconsider. IEEE 1547 reduced barriers to DER deployment while ensuring that the stability and resilience of power system were maintained. Okay. So this is what is scope of this standard. IEEE 1547 specified technical requirements for DER interconnection with area electric power system. So you see, here you have area electric power system, and here you have distributed energy resource. So the interconnection between the two, power interface is there, but it has to have communication interface also. Transfer of data and communication, an operator and those things. It primarily applies primarily to installation with capacity less than 10 MVA. Okay, covering power quality, protection system, anti-islanding, fault handling, performance requirement, right through, dynamic response, communication and monitoring. Okay, the scope includes diverse system, PV, wind, storage, microgrids. 10 MVA, less than 10 MVA. So key technical requirements in power quality like voltage regulation, frequency support. Okay, so DER must adjust real power output to help stabilize system frequency. Like DER must regulate voltage within specified range using reactive power control. So earlier it was not there. Harmonics, total harmonic distortion, the IEEE 519 we have already discussed. Voltage and frequency abnormal conditions. IEEE 1547 defines maximum disconnect times for abnormal voltage and frequency conditions. Then you have protection function, then you have dynamic response to disturbances. Voltage right through. Okay, so here see, 1547-2003 DERs were required to disconnect rapidly during grid disturbances. 2018 revision mandates right through capability, which is a very good thing. DER must remain connected within a specified voltage profile, supporting the grid instead of abandoning it during the abnormalities. This prevents cascading outages and contributes to system. And now we cannot afford it also that you disconnect because more than 50% is coming from renewable energy, right? So if you see this voltage per unit, it is time. So this is the limit. Although, so minimum voltage limit is this. I will tell you how much it is. Maximum voltage limit is this. And mandatory right through. So within this range of voltage at the grid, DER should remain connected. While here in this region, if they want, they may trip. Frequency right through. Why they have not written here? I think later on we will see that is around 1.1 and this is 0.95 or so PU. Frequency right through. So this is the maximum frequency limit, which is 63 Hertz. First, we are talking about North America, 60 Hertz. And this is the limit, minimum frequency limit of 57 Hertz. 57 Hertz here and 63 Hertz here. So in this period, mandatory right through zone, you cannot disconnect if the variation of frequency within this range and the DER should support the grid. While here, if they want, they can trip in this region. Volt-var control function, DER inverters provide dynamic reactive power support. As I told you that 50% of capacity is used only for interphasing power, but the rest of the capacity they should use for reactive power compensation. At low voltage, DER supply reactive power, positive wire. See here, this is voltage and this is reactive power. Low voltage in this region. After 0.95, you can say that reactive power has to be supplied by DERs for low voltage supply. High voltage, they absorb reactive power. So here they are working as a capacitor and here they will work as an inductor to absorb the negative wire in this range. 1.050, 1.05 and 0.95. So this is the voltage range. So perhaps that was the voltage range there. Okay, 0.95 and this is 1.05. Okay, frequency watt group control. If frequency decreases, DER increases power output or curtail less power to support. This is what in China they were doing. Because in China, there is so much renewable energy integrated to the grid, they have voltage instability. So all the time they are talking about curtailment of renewable energy sources to reduce the power injected by renewable energy to the grid. So this is what I was there in a conference, one-day conference organized by a company, and they produce this vanadium redox battery storage system. Vanadium redox, generally we have the idea that it has low power density, but it has the more retention. Their leakage of electricity is less, and it is cheaper also. So that company is making. So what they were producing, what they were proposing, that we should put large size vanadium redox boxes of batteries around the city to charge the battery, so that we have to do less curtailment of renewable energy to make the grid stable. So this was actually the point they were making. So frequency decreases, DR increases power output or curtail less power to support grid recovery. If frequency increases, DR reduce power output to restore balance. So here you see the standard state that DER must cease to energize within the threshold shown in the table. Okay, if voltage range is less than 50% of nominal, maximum clearing time 160 millisecond. So DER must disconnect within 160 millisecond if voltage on the grid is less than 50%. Okay, if it is between 50% and 88% voltage range on the grid, then within 2 seconds it should disconnect. If voltage range is between 110% and 120%, then 1 second clearing time. And if voltage is more than 120%, then 160 milliseconds they should disconnect. So this is the maximum clearing time for DER less than 30 kilowatt. Default clearing time for DER more than 30 kilowatt. This is the default clearing time, and this is the maximum default clearing time for DERs more than 30 kilowatt, and if DER is less than 30 kilowatt, this is the maximum clearing time. Similarly, the frequency range, you can see if the frequency is more than 60.5, so DER should get disconnected in 160 millisecond. If the frequency is less than 57 Hz, then 160 millisecond. If it is between 59.8 and 57 Hz, adjustable between 160 millisecond and 300 second. So if DER is less than 30, so this is the frequency. If DER, so you see this is for DER for more than 30 kilowatt. IEEE 1547 allowed adjustable trip time for DER above 30 kilowatt, but units may trip earlier than the threshold. Vendors often use tighter settings to meet. There is some other standard for anti-idling. So we should not concern about this. Figure shows the voltage disconnect requirement with DER tripping in the red zone. So DER should trip in this red zone. What is this? This is the voltage percent of nominal. So you see, this is IEEE 1547. So at least in this region, DER should remain connected. In fact, DER typically operate within NC range A or range B, okay, under steady state conditions. So all the time they should remain connected. And they may remain connected in this region also, but if they want to trip, they can trip. And this is very fluid, this may be tricky. So basically, they should operate most of the time in this region. So, but you should see the timing. The timing for this 0.16 second, it means 160. This is what we saw, 160 millisecond, right? And here see the timing and the voltage requirement. Now there is NERC, which is North American Electric Reliability Corporation, and it has protection and control standards. So NERC has its own standard. FERC, Federal Energy Regulatory Commission, it has its own standard. So you see, different people, they have different standard. But this IEEE 1547 is this. So in this region, it must trip and clear, while in this region, it may remain connected. But according to NERC, see, there is a conflict here, basically, because different agencies, they have different pressures from different industries. So they try to make a standard to satisfy those big companies and those things. But IEEE 1547 is, I think, is unbiased. And then there are other standards anyway. And then there are communication and those things, wide area network, but these are communication things, we don't know about this thing. So this is what it is. Okay, I will stop here. You can read it, there is nothing special to read here.